Good afternoon to all of you. This is lecture 17 in thermodynamics course. So now in the steady flow energy equation. So lecture number 15 and 16, I have covered the steady flow energy equation. That is how you can apply the steady flow energy equation for various mechanical systems. Steady flow energy equation for mechanical systems. So there are what are the applications are there. So if you observe you can apply the steady flow energy equation for turbine, compressor, blower, right? Motor, pump. Next one is the heat exchanger. So that is the direct contact heat exchanger, indirect contact heat exchanger, uh, different types of compressors. Next one is the throttle valve, right? So in throttling process, next in case of nozzles and diffuser. So all these are nothing but the examples. Even for you can apply the steady flow energy equation for steam power plant, hydro power plants. Next one is nuclear power plant, right? So wherever you may, whenever there is a mass flow rate entering into the system and mass flow rate leaving from the system, and the energy interactions are taking place from the system to the surroundings, so that it is nothing but the open system. Now, in this class, what the outcome from this particular content is, in the 16th video lecture, I have covered the building or developing the heat and work transfer relations for open system when it is subjected or when it is undergoing in various process. So that is applying the first law. Now this is the 7th video lecture, and this content, e-content is developing uh, in association with Andhra Pradesh State Council of Higher Education and the JNTK Kakinada. JNTK Kakinada. So, but before that one, once again, I recapitulate the things connected to the steady flow energy equation. So, in steady flow energy equation, the control volume technique is almost control volume technique you have to apply. Although the system approach is quite valid, there is another approach which you can find it in a highly convenient mode. That is sometimes we may get the doubt that is where I need to concentrate, in open system or in closed system. In what way? So instead of concentrating attention upon a certain quantity of a fluid, so instead of concentrating upon a certain quantity of a fluid which constitutes a moving system in the flow process, but attention is focused upon certain fixed region. So attention is focused upon certain fixed region in space is called the control volume. See this one. Observe the control volume. And what about the dotted line? This is the control surface, and this you can call as a moving. This you can call as a boundary of the open system. So this is all the control volume. So just instead of focusing onto the fluid flow behavior, if you focus on to the certain fixed region in space is called the control volume, through which moving fluid is entering and moving fluid is leaving. So this is like the same analysis you can apply it. That is in fluid mechanics, the Eulerian approach. So this is like the analysis of Eulerian in fluid mechanics, right? So in fluid mechanics, we are going to study the Lagrange behavior or Lagrange's approach and Euler's approach in fluid mechanics, right? Um, Next one is to distinguish between the two concepts. So what about that one? Two concepts means whether it is a closed system or it is a open system. Closed system or open system. That is the closed system boundary usually changes the shape. In case of a closed system, the boundary usually changes its shape position, and also orientation relative to the observer. Whereas the control volume boundary, see, the control volume boundary remains fixed and unaltered. Again, while the matter usually crosses the control volume boundary. Again, so this is the control volume boundary. Matter usually crosses the control volume boundary and no such flows occurs across the system boundary. So here the broken line, that is this dotted line, represents the surface of the control volume. This represents the surface of the control volume, which is known as the control surface. From the control surface, mass transfer is taking place and also energy transfer is taking place. So this is the same as the system boundary of the open system. So this is known as the boundary of the open system, right? Hope you understood the control surface, boundary, control volume, and control mass. So all these are connected to the various systems. So at the steady state of a system, the thermodynamic property will have a fixed value. The thermodynamic property will have a fixed value. So how you can focus onto that one? So here, this is the system, and here the thermodynamic that is thermodynamic property. Say if it is a P1 or V1 or T1, so we'll have the fixed value at a particular location. We'll have the fixed value at a particular location and will not alter with respect to the time. So that's why we are calling it as a steady flow. This steady flow energy equation, there is a TFE as also there. TFEE, that is transient flow energy equation, or you can call it as an unsteady flow energy equation. But in your syllabus, only you have the steady flow energy equation, and I am going to discuss that steady flow energy equation. Actually, in thermodynamics, there is a transient flow energy equation is also there. But for higher studies, where this particular application is, this particular equation is used for higher studies, that is PG level and PhD level. That is the transient flow energy equation. And you can also call it as a unsteady. You can also call it as a UFEE, unsteady flow energy equation. Unsteady flow energy equation. So the thermodynamic property may vary along the space coordinate. The thermodynamic properties may vary along the space coordinates, but do not vary with respect to the time. So whatever it may be the time, but here also that is the same P1. Whatever it may be the time, here also the same volume. Whatever it may be the time, here also it is the. So steady state means that the state is steady or invariant with respect to the time. State is steady or invariant with respect to the time. So this is what uh, you have to observe in this particular. Now, here the question is that after studying this, here there is a difference that you have to find. So, what is that particular difference? What is that particular difference? So, when you write the equation, that is here, when you write the equation, that is m dot into, that is if you write it as in terms of this u1, that is small u1 plus small u1 plus small v1 v1, right, plus kinetic head. Let me write it as a c1, that is c1 square by 2 plus gz1, that is potential head, plus here d bar q by dt, d bar q by dt, right, d bar q by dt, that is nothing but equal to m2 dot u2 plus P2 V2, that is this is the flow work and the kinetic energy at the exit section of a pipe plus the datum head at the exit section plus d bar w by t, d bar w by t, right? So d bar w by t. And here what you should have to understand is that the energy flow rate per unit time. So this is energy flow rate. Energy flow rate per unit time. So this is you can consider it as a energy flow rate. Energy flow rate per unit time, right? And that energy flow rate per unit time where you are going to apply. So this is more convenient only when a single stream of a fluid. This is more convenient only when that is single. So the energy flow per the basis of energy flow per unit mass is the basis of, that is here single stream, and two things that you have to observe. One more point, that is M1, that is here let me, sorry. So this is this is nothing but equal to H1. So here H1 plus C1 square by 2 plus G Z1 G Z1 plus d bar q by dm is equal to H2 plus C2 square by 2 plus GZ2 plus d bar W by dm. D bar W by dm. The basis of energy flow per unit mass. So this is a basis for energy flow per unit mass is more usually convenient when only a single stream of a fluid enters. When this is more convenient, this is more convenient when a single stream. So when a single stream of a fluid, single stream of a fluid, uh, when only a single stream of a fluid enters and leaves the control volume. When more than one fluid stream is involved, then the basis for per unit time is mentioned. So this is more than, this is used for more than single inlet, more than single inlet, right? So the energy flow per unit time, this is generally more convenient to use it for uh, when more than one fluid stream is involved, basis of energy flow per unit time is convenient, right? So this is more than um, single fluid or more than single fluid. In that case, the time is mentioned. But in case of a single stream, then you can use this particular equation. You can use this particular. So now you have to apply this particular steady flow energy equation for solving the numerical cases. Now come to the problems. So here there the problems are there. So now look at this particular problems. So one by one here. Now there is the first question is that air flows steadily at the Air flows steadily at the rate of 0.5 kg per second through an air compressor. See, observe this one. Air compressor. It is also one of the application of a steady flow energy equation. Application of it is also the open system. Open system, right? One of the application of a steady flow energy equation. Air compressor entering velocity 7 meters per second and 100 kilopascal, that is P1, and 0.95 meter cubed per kg volume. So small V1, and leaving at 5 meters per second, that is velocity and pressure P2, and the volume 0.19 meter cubed per kg. 0.19 meter cubed per kg. The internal energy of the air leaving is 90 kilojoule per kg, greater than that of the air entering. Cooling water in the compressor jackets absorbs the heat from the air at the rate of 58 kilowatt. So the things what you have to calculate is compute or calculate the rate of shaft work input to the air in kilowatt hour, that is in kilowatt. Second one is find the ratio of inlet pipe diameter to the outlet pipe diameter. Find the ratio of inlet pipe diameter to the outlet pipe diameter. Right? So this is the given problem. This is the given problem. Now you can write the diagrammatic sketch. So that is when air compressor is mentioned. When air compressor is mentioned, so try to draw the small representation. So it's a good practice.